Hello, and welcome to Lecture 4 of Magnetic Forces and Fields in PHYS 1201. We spent last lecture looking at the magnetic forces on currents in wires. Now we're going to look at the magnetic forces on charges that are moving outside of wires. A current is nothing more than moving charges, and so unsurprisingly, you're going to find a lot of this lecture pretty familiar, because a lot of this works the same way as it does for forces on current-carrying wires. So the magnetic force on a moving charge is perpendicular to the velocity of the charge and perpendicular to the B field, and it follows a right-hand rule. So this time you put the velocity vector along your thumb and the B field along your index finger, and your middle finger now gives you the direction of the magnetic force. So if you try that with this charge, you may have to contort yourself a little bit to arrange your fingers the right way, but you will find that the magnetic force here is out of the page. Now, the only other complication is that if the charge is negative, then you have to reverse the direction of the magnetic force from what the right-hand rule tells you. So for example, here we have a B field out of the page and a negative charge going this way. And again, you may have to contort yourself a little bit to do the right-hand rule, but if you do, you're going to find the right-hand rule says this way, but now because this is a negative charge, you have to flip it, and the force would be in that direction. And the magnitude of the force on a charge works in almost the same way as well. Just as for a force on a wire, there's a sine theta that comes in, and so you get the largest force when the velocity is perpendicular to the magnetic field. And the only other thing to watch out for is that because this equation is giving you a magnitude, you should use the absolute value of the charge here so that you don't have an extra negative sign floating around to confuse you. Let's use this to calculate something again. So let's suppose we have a solenoid. So this is the end view of a solenoid, and it's got a current running clockwise or counterclockwise from our point of view. And this is 400 turns of wire in this solenoid, and it's 10 centimeters long. And here we have an electron. Perhaps we have a beam of electrons passing through, and they are going this fast, 5 times 10 to the 7 meters per second, which may seem very fast, but for an electron that's actually pretty sluggish. And let's now work out the force on one of these electrons. So first of all, we should know about the B field inside the solenoid. Let's get the direction first. So the right-hand rule, again, is going to tell you that the B field inside the solenoid is out of the screen. So now we know the direction. Let's get the magnitude. I'm just going to take this and I'm going to plug the numbers in. And I get a field of 2.5 times 10 to the negative 2 Tesla. That's a pretty strong field, but a fairly large factor smaller than what you would get from rare earth magnets. And just check that the units work out. It is Teslas. Now, let's figure out the force on the electron. So, use the right-hand rule again. And so you stick your thumb along the velocity vector and your index finger along the B field. And the right-hand rule now has your middle finger pointing up, but this is an electron, and so that's negative, and so you have to flip that. And so this force should be down. Now that we know the direction, let's get the magnitude. That's going to be pretty easy, because note, V and B are perpendicular, and so again, our sine theta is going to be 1. And so all we need to do is our QVB. And we get 2 times 10 to the negative 13. And just check the units. A Tesla is a Newton per amp meter. And so here we have meters, canceling meters, and coulombs per second is amps, so those cancel the amps, and we get newtons as we have to. That may seem like a very small force, but remember, this is an electron. Its mass is of order 10 to the negative 31 kilograms, and so this will cause an absolutely gigantic acceleration. Let's now think about the effect that this would have on the electron. Note that we have a force which is always perpendicular to the velocity. If it bends the path, which it will, then as the velocity vector changes direction, the force vector will change as well to stay perpendicular to it. And remember, when the force is perpendicular to the velocity, it has no effect on the speed. So this electron will move with constant speed. And it's moving inside a constant magnetic field. And so with a constant speed, a constant magnetic field, and the velocity always perpendicular to the magnetic field, that's going to give a constant force, magnitude, perpendicular to the velocity. Well, we know what this does. This is going to be uniform circular motion. And so this electron is going to go in a circle. Well, let's find the radius of that circle. We know then that the FB is the only force acting on this electron, and so that is the net force. And the net force in uniform circular motion is equal to mv squared over r. So we can find the radius of the circle just by so let's plug in all the numbers. And we get that the electron is going to go in a circle a little over a centimeter in radius, about 1.1 centimeters.